All right, here is problem 81 on page 186. It is a sister to your assigned problem 84. In both cases, we're analyzing polynomials. We're taking the equation and we're essentially drawing the graph. And your book has a procedure. Sort of go to the shelf and pull down the procedure here in order to do this. You can find that summarized in a yellow box on page 181. I'll let you look at that, but let me just remind you essentially what that procedure is. And there's really no, this is a procedure, but the order is, in this case, not really that important. They call out in the first case, let's go determine the end behavior. Let's just note how the function is behaving as x gets very large. The absolute value of x gets very large, so x gets large, positive or negative. Pull out and find the x-intercepts, pull out and find the y-intercepts, and then not only find these x-intercepts, but determine what the multiplicity is, because from the multiplicity, for odd multiplicities, the graph of the functions cross, if it's odd, and they touch if it's even. So that'll appear in this particular problem. So let me talk about that a little bit later on. It's worthwhile to determine what the maximum number of extrema are, just to sort of check yourself. And from this, you can sort of draw a skeleton in some ways. You can sort of start to sketch out, I'll call it a skeleton sketch, how the function is going to behave, how the graph of the function is going to behave. And then you might need to plot a point or two. Before you then complete the graph, all right? So let's kind of go through this for this particular problem, x squared times x minus 3. So the first thing to do is let's check off this end behavior. This is, if we were to expand this out, it's nice that f is given to us in factored forms. It's going to help with x-intercepts immensely. But you really need to think of it both in this factored form and totally expanded and in sort of the standard form for a polynomial. And that standard form then is x cubed minus 3x squared. There's the polynomial in all of its glory. And when you see it in all its glory, what you want to take note of is the coefficient on the leading term, because it's that leading term that determines the end behavior. What you can see is that as x gets very large, this polynomial tends to look like x cubed. And so you can come right here, right now, and sort of sketch in an x cubed. And the function is going to wiggle around near the axis, but then it's going to kind of align itself really in an asymptotic fashion towards this x cubed. So we've done the first thing. We've determined the end behavior, and we've drawn this little graph in this manner. The next thing is determine the x-intercepts. And the x-intercepts, clearly, you can see them right here by inspection. They're x equals 0 and x equals 3. These are the numbers that make f of x equal to 0. These are the points at which the function crosses or touches the x-axis. But beware that not only do you have to determine the what the values are, but you have to determine their multiplicity. The multiplicity of this 0 at x equals 0 is 2. And the multiplicity of this root, x equals 3, is 1. And that means that the graph is going to touch here. It's going to cross here. And you can kind of make that clear to yourself by plotting the point 0, 0, and giving yourself little sketch that says, it's either going to come up like this or it's going to come down like this, one way or the other. It's not going to cross the axis, it's going to kiss the axis. And you can come over and plot this point right here. This is the point 3, 0, one of the roots. This is the point 0, 0, another one of the roots. And in this case, it's going to cross. So the graph is either going to do this or it's going to do something like that. Yeah. So that's just a reminder to yourself. You have plotted 2 points of the graph here, and we've completed that. Quickly, y-intercepts occur where x is equal to 0. And when x is equal to 0, you can see that the y-intercept, or at least the y-coordinate of the y-intercept, is 0, 0. So the y-intercept is the point 0, 0, which we've already plotted. It's not, it's a little unusual for the y-intercept to be a 0, but not unheard of. Maximum number of extrema. Let's take care of that quickly. If this is a third-order polynomial, there are at most 2 extrema. You're going to end up seeing a graph that looks like this, or a graph that looks like this, or maybe a graph that looks like this that has no extrema. You're either going to have 2 or you're going to have 0. All right, so we've done that. And we've now sort of, by virtue of that, we've also done this skeleton sketch. We know now that the function has to end up down here. It has to go through this point and just touch. It has to then drop into a negative area and reach up through this point. And so I'm kind of ready to draw it. If I want to get a little bit more accurate, let me try a point or two. Let me just try, x is equal to 2, and let's see what we get. If we put in 2, you get 4. 2 minus 3 is minus 1. You get minus 4. So the point 1, 2 minus 4 is also a point on the graph. So I'm really ready to kind of sketch this thing now. I'm going to come up like this. I'm going to touch at that 0. I'm going to touch at this point. I'm going to go rolling up through here, and I'm going to end up aligned with this this end behavior. So the more points you make, the more accurate you can make the graph. But I think this is sufficient.